Gondwana was a huge supercontinent during the Ordovician. 3 other continents were still independent and stayed independent throughout the period. These continents were Laurentia, Siberia and Baltica. The mid to early Ordovician saw warm conditions. This may be due to elevated CO2 levels which were caused by volcanic activity seen in the Cambrian, or it may also be due to large open seas and the lack of ice at the time. Ordovician time showed the highest sea levels of the Paleozoic. Laurentia and Gondwana were surrounded by shallow seas which encouraged organism growth. By the late Ordovician, Laurentia and Baltica moved closer together. At the beginning of the late Ordovician, volcanoes along the margins of the Iapetus Ocean spewed massive amounts of CO2 into the atmosphere, turning the planet into a hothouse. The volcanic emissions from the Iapetus margins stopped by the end of the late Ordovician. The Ordovician sea level more or less rose throughout the period, levelled out by the mid-Ordovician and drastically dropped by the end of the late Ordovician. The drastic drop in sea level was a result of Gondwana taking up a position over the South Pole and glaciation taking place.
The terrestrilization of plants is one of the most significant events in the history of the biosphere, as we know it. This changed the composition of the atmosphere, soils, how continents eroded, and not to mention paving the way for terrestrilization of animals. One proposed reason that plants managed to successfully ascend to land at this time has been attributed to oxygen concentrations. Increasing the amount of oxygen in the atmosphere allowed the planet to produce more ozone, which in turn decreased UV radiation, allowing for a safer transition from the marine realm. 2 main theories have been put forward for the manner with which plants successfully made it onto land. The first is a direct marine-to-land transition. The second, and far more likely, is a marine-to-land via freshwater transition. This second theory is supported by the oldest known terrestrial plant identified through its spores. These spores were discovered in a sedimentary rock, which would have originally been an estuarine-type environment. With this unfriendly new world ahead of them, plants had several obstacles to overcome. The first of which was the manner with which they reproduced. Algae reproduce through spores, which move through the water column and fertilize other algae. On land, a hard shell is needed to protect the spores from damage and from UV radiation. With the increasing size of terrestrial plants, a vascular system was necessary to transport water and nutrients up and down the plant. In turn, this meant the development of a wax cuticle to stop desiccation. With this impermeable layer, it was necessary for a pore space which could be controlled to allow gas exchange in and out of the plant. Fluids being a limiting resource, it has been hypothesized that plants would have been found in close proximity to water. For this reason, it has been hypothesized that they would have been small and somewhat similar to modern-day hornworts, liverworts and mosses. This covering of near water areas led to the creation of soils, a new food source, and a change in the environment. This paved the way for marine animals to colonize land.
Within the Silurian, Gondwana continued a slow southward drift to the high latitudes. There is evidence of Silurian ice caps, but they were much less extensive compared to those of the late Ordovician. The continents of Baltica and Laurentia came together to form a second supercontinent called Euramerica. This event caused the Caledonian orogeny, which stretched between the Baltica and Laurentia continents. These 2 continents coming together saw the end of the Iapetus Ocean. By the middle of the Silurian, global climate had become warmer, comparable to that of most of the Ordovician and Devonian periods. The majority of the Silurian saw much more stable climate conditions compared to that of the previously explained Ordovician. The warm greenhouse phase in the Silurian promoted life in warm shallow seas, which are seen around much of the equatorial landmasses at this time period.
Today, the diversity of animals on land exceeds that of the sea, with insects making up 70% of this diversity. But it wasn't always like this. No phylum originated on land, and the first animals to appear on land were the invertebrates, sometime in the Ordovician, less than 500 million years ago. There were many obstacles associated with the move onto dry land. Fertilization, which was easily accomplished in the water, posed a new challenge on land. Other mechanisms for sexual reproduction were conceived. Moving from the highly supportive aqueous realm to the unsupported atmosphere was highly problematic, with the invertebrates having to improve or evolve supportive structures. The difference in refractive index between water and air posed a major optical problem for the first land dwellers, having to drastically change ice structure. Sound is more important in open air than in water, as high frequency vibrations can be detected easier here, so the auditory organs were adapted. New breathing apparatus had to be developed, as the partial pressure of oxygen in water allowed it to be more easily assimilated than in the open air. Finally, to achieve the true conquest of land, organisms had to become homohydric, enabling them to maintain permanent internal hydration, mainly by having waterproof cuticle or skin. Proof of the conquest of land comes in two forms: trace fossils and body fossils. Trace fossils. These fossils represent the earliest evidence for terrestrilization and appear in the Ordovician. Trackways found among the subaerial deposits of the Caradocian Borrowdale volcanic group of northwest England may have been produced by animals making limited excursions onto land, and may even have been fully terrestrial. Meandering subvertical backfill burrows in an upper Ordovician paleosol in Pennsylvania resemble modern-day millipede burrows, such as this cast here. Coprolites, bearing plant remains, provide direct evidence of early plant-animal interaction. In the Welsh borderlands, paleontologists have found coprolites packed with different spore types, known from Silurian and Devonian sites. Body fossils give direct indications of the type of animal present, but it may not be clear whether or not they lived in the terrestrial environment, though the nature of the sediment may prove a good indication.
Trigonotarbid's are the extinct relatives of spiders and are among the oldest land animals. Examples are found in the late Silurian formation in Shropshire and exhibit terrestrial features like buck lungs. Good millipede and centipede fossils occur in the late Silurian and Devonian strata, including scuti geromorph centipedes. Scorpions succeeded in terrestrialization by converting their gills to lungs. The oldest scorpion with buck lungs appear in the lower Devonian, but semi-terrestrial or amphibious forms probably existed before this. The Devonian period was a time of great tectonic activity as Euramerica and Gondwana drew closer together. This is the first steps towards assembling Pangaea. This activity further raised and extended the Caledonian Mountains. Sea levels were high worldwide and much of the land lay submerged under shallow seas. The Devonian was a relatively warm period and probably lacked any glaciers. However, CO2 levels dropped throughout the Devonian period due to the burial of the newly evolved forests, drawing carbon from the atmosphere and into the sediments.
The terrestrialization of tetrapods appears to have taken place sometime in the Devonian period, where descendants of the lobe-finned fish, like Euceropteron, required various adaptations, enabling the conquest of land.
The oldest clues we have to suggest when this move onto land first began comes in the form of trace fossil trackways. Here in Ireland, we have our own tetrapod trackway located in the southwest of the country on Valentia Island. This trackway is dated as being 385 million years old and was, for some time, the oldest known tetrapod trackway. Although a recent trace fossil discovery in a quarry in Poland has removed the title of oldest tetrapod trackway from Ireland, with this new trace having been dated as being 397 million years old, pushing the time of terrestrialization back some 20 million years. The Poland trace not only pushes back the date, but seems to have drastically changed the previous hypothesis of a move onto land from a freshwater source, as the paleo-environment of this quarry in Poland indicates that of a marine setting, suggested by the presence of stromatolites, conodons, and shrimp burrows. Desiccation cracks are also present, suggesting periods of sub-area exposure.
The question remains, what did the creatures that made these strata look like? Various fossil fragments of Devonian tetrapods have been found, such as Acanthostega and Ichthyostega, as well as transitional forms such as Tiktaalik.
Artistic representations provide an insight as to what the creatures responsible for these traces would have looked like.
This shows the implication one fossil find can have, and who knows what we discovered as older Devonian rocks are examined more closely.
Trace fossils. These
Sometime in the Devonian period,
and other things which are bad.